This lesson on pressure vessels, otherwise known as air vessels, aims to give a sound appreciation of the workflow required to design a system surge protection using pressure vessels. The 3 steps in the design process are 1. Analyse the initial air volume required. 2. Determine the total capacity required for the pressure vessel. And 3. Finally tune the vessel's inlet-outlet piping arrangement to suit the dynamics of the water system. Quantifying the initial air volume needs to be the first step because it is the parameter that defines the amount of stored energy available to protect the water system. Actually, it's the initial air volume plus the initial hydraulic level that govern the amount of stored energy. The initial hydraulic level, however, is usually predetermined by the water system's steady-state hydraulics. The second step in the design process is to match the pressure vessel's total volume, height, and initial water level to the range of water levels that will occur during transient events. The aim is to make sure the vessel does not empty during surge events. During this step, the designer typically keeps the same initial air volume and adjusts the total capacity of the vessel to provide more or less water volume. The third step involves selecting the size and layout of the inlet-outlet pipe connecting the pressure vessel to the main line that the vessel is protecting. In some systems, it is suitable to use a plain pipe connection between the vessel and the water main. In other systems, it becomes necessary to dampen the interaction between the pressure vessel and the fluid system by applying differential head loss to the inlet and outlet paths. This is typically achieved by installing a large, full line size, non-return valve with a small diameter bypass around the non-return valve. On projects installing a pressure vessel on the pump delivery side, the non-return valve allows unrestricted flow out of the pressure vessel. In effect, this arrangement ensures that the pressure vessel only delivers stored energy into the pipeline when the pipeline requires additional energy. On projects installing a pressure vessel on the suction side of a pump station, the same arrangement is used except that the non-return valve is reversed. This arrangement allows the pressure vessel to absorb energy without restriction. Let me tie this together in the context of a typical example. Here we're looking at a simple pumping main. It is a 1,000 mm diameter mild steel cement lined pipeline, 3.5 kilometers long, transferring water from a low tank to a high tank. The system has a static lift of 50 meters. The flow rate is 717 litres per second, which means the steady state velocity is just below 1 metre per second. We will be simulating the pump power failure scenario. With an initial velocity of 1 metre per second in a large pipeline, we are considering a system with substantial momentum in the water column. Our example demonstrates the steps required to design a pressure vessel on the delivery side of the pump station. Note to model various inlet-outlet connections to the pressure vessel. There is a non-return valve and a simple restriction valve. This arrangement allows the head loss through the simple restriction valve to be adjusted to simulate various sizes of small diameter bypass around the non-return valve. First, here are the results of a simulation of the system without any surge protection. We are looking at the envelope of transient heads along the pipeline from the pump station on the right to the high tank on the left. Looking at the initial hydraulic grade line, shown in red, note that there is very little friction loss in this system. As we will see later, the lack of friction plays a big role in the dynamics of this system. Without any surge protection, this pipeline suffers negative heads throughout its entire length after power failure. And in 2 locations, vapor pressure is reached. Maximum transient heads, however, are acceptable at 95 metres and lower. In this example, assume we are looking at a steel pipeline that has been installed with only Class 12 flanges, fittings, manholes and valves. As a result, consider the maximum permissible working head to be 120 metres in this system. Conclusion: the system requires surge protection to prevent negative heads forming in the pipeline. After a number of trial simulations, it was determined that the required initial air volume is 0.5 cubic metres. Now we are looking at the envelope of transient heads along the pipeline following power failure with a pressure vessel installed, starting with 0.5 cubic metres of air volume and connected to the pipeline with a plain pipe connection. From this profile and the transient head envelopes, we can conclude that the pressure vessel has eliminated unacceptable negative heads along the pipeline. However, by adding the stored energy of a pressure vessel to the system, the maximum transient head in the system has increased. At a maximum of 150 metres, this outcome is unacceptable. Adjacent to the pump station, it exceeds the Class 12 pressure rating of the pipeline. Satisfied that 0.5 cubic metres is the appropriate initial air volume, step 2 of the design process is to look at the amount of water available in the pressure vessel. In this presentation, I will only show the initial unsuccessful trial run. By tracing the water level in the vessel and defining the vessel's top and bottom levels, it's very easy to evaluate the quantity of water required in the vessel. This graph shows that the initial trial size is too small. It will empty 3 seconds after pump power failure. Obviously, I need to increase the size of the pressure vessel while keeping the same initial air volume. There is little value in demonstrating the trials used to increase the physical side of the vessel in this example. After several trial runs, a total vessel capacity of 1.75 cubic metres was chosen. That is, prior to a power failure, the vessel contains 0.5 cubic metres of air and 1.25 cubic metres of water. Let's move on to step 3, which sizes the inlet-outlet configuration between the pressure vessel and the pipeline. From a previous simulation, it is known that a plain outlet connection is not suitable. Here we are looking at the results from a trial simulation with a line size outlet non-return valve and a very small diameter bypass around the non-return valve. This configuration still protects the system from negative heads. At the same time, it reduces the maximum transient heads. A maximum head of 100 metres is well within the Class 12 pressure limit of the pipeline. To further explore the influence of the diameter chosen for the non-return bypass pipe, here is another trial simulation using a slightly bigger diameter bypass pipe. Again, acceptable surge protection against negative heads is provided. Slightly increasing the size of the bypass pipe around the non-return valve has lowered the maximum head experienced by the system. However, don't expect a simplistic linear relationship between bypass pipe diameter and maximum surge heads. Remember, we are dealing with a dynamic system where timing of events is relevant. Always do sufficient trial simulations to define the characteristics of your inlet-outlet arrangement. Let's use the simulated results of pressure vessel water level and its inflow-outflow rate to gain further insight into the dynamic behaviour of the system. A pressure vessel with just a plain connection between the pipeline and the vessel has a very dynamic resonant response. Water level in the vessel oscillates up and down, rapidly and regularly. Recall that the pipeline offers very little friction loss to attenuate the energy available during surge events. Highlighting the zero flow line on the graph, note how the vessel's flow rate oscillates between substantial outflow and inflow. Using a plain connection on a system with high water momentum and little friction loss is not a good idea. This combination creates a highly resonant system, plus the vessel's stored energy help to exceed the pressure rating of the pipeline. Now connect the same pressure vessel with a large outlet non-return valve and a medium diameter inlet bypass. We see a much different dynamic response inside the vessel. Water level drops initially, then rapidly recovers and stabilizes. Cyclic opening and closing of the non-return valve may not be desirable from the perspective of wear and tear on the valve. In this arrangement, the non-return valve enables the pressure vessel to supply energy to the pipeline only when the pipeline needs that energy. The small diameter bypass acts as a dampener in the system. Looking at the case with a very small bypass pipe around the non-return valve, we see an even more stable behaviour. The pressure vessel delivers flow into the pipeline immediately after pump power failure, then only delivers very minor flows at about 2.5 minutes after pump power failure. Water level in the vessel drops initially and progressively recovers and stabilises. Considering the overall set of results, I would adopt the pressure vessel inlet-outlet configuration using the small inlet bypass diameter. It gives acceptable surge heads within the pipeline. Negative heads are prevented. Maximum heads stay within the pipe's Class 12 pressure rating. Plus it provides stable behaviour within the pressure vessel. Each system will be slightly different. Despite this, the 3 steps in the design process are always the same. First, select the initial air volume. It determines the degree of surge protection the system needs. Second, assess the total vessel capacity required to prevent the vessel emptying and discharging air into the pipeline. Finally, run a series of simulations to size and tune the piping connection between the pressure vessel and the main pipeline. Thanks for watching. Now please take a few moments to consolidate the key messages and review what you have learnt in this lesson.